Hi students, and welcome to Preliminary Chemistry and the Chemical Earth video series. We're going to look at covalent networks this time in our last little series on linking structure to chemical properties. In the previous video we looked at ionic structures, so now we're going to look at covalent networks. Covalent networks exist in both elements and compounds, so something like carbon in its diamond form, and also silicon, and compounds like silicon dioxide or silicon carbide all demonstrate this process or this property, structure indeed, of covalent networks. And covalent networks exist in the same way, I guess, as we were looking at our ionic networks, with two major differences. Number one is the number of bonds surrounding each of the individual atoms, and also the fact that they are atoms and not ions. They're not charged. All of these are covalent, so they are bonds which are sharing electrons. And so the 3D networks will contain a series of carbons, for example, in this case, all bonded to each other by covalent bonds. Now, carbon bonds in a tetrahedral arrangement, it likes to have 4 bonds. It has 4 electrons, so therefore it forms 4 electron pairs. So you get these tetrahedral structures existing in all directions, and that's how the crystal grows. In something like diamond, this structure is incredibly hard and stable. So there's some very important properties that link to these covalent networks. If we have a look at something that kind of just roughly represents diagrammatically what I was looking at before, where each of these individual black marks would be a carbon atom, then you can see that each individual carbon atom is bonding to other carbon atoms in those 3 dimensions, again, as we've talked about before. All of the bonds in this case are covalent bonds, and covalent bonds are a type of chemical bond, and again, ones that are very strong. So for something like diamond, there's no weak point within the crystal structure. Now, carbon does exist in another form called graphite, as well as some other things we'll look at later on. And so that structure is slightly different. Certainly graphite is a lot softer than diamond and has a few other different properties as well. But if we think about covalent networks as being continuous array of atoms in all of the 3 dimensions, as the crystal grows, it gives us a very regular shaped crystal. And this regular shaped crystal is based on very strong bonding between each of the individual atoms. So that gives us a few very important properties. Firstly, these covalent networks have very high melting and boiling points. It takes an enormous amount of energy to break those covalent bonds. And of course, we have to have them at least free enough to slide past one another in the liquid phase and obviously move independently in the gas phase. So this requires a huge amount of heat. We said previously that conductors are based on freely moving charge, and there are no ions, and the electrons are all held up tightly within the bonds. So because there are none of these, then there is no opportunity for this particular substance to conduct electricity or heat. They're extremely hard, but also very brittle. They will crack if they're put under pressure. The bonds will just split apart. And there's a level of chemical inert or non-reactive capacity or property for many of these compounds. Now, of course, we know that carbon will react with oxygen, for example, so it's possible you could put a diamond into some liquid oxygen, produce some really nice carbon dioxide, but it'll be fairly expensive carbon dioxide at that. The other thing about most of these covalent networks is that unlike most ionic substances, or at least a range of ionic substances, covalent networks are insoluble in water. There's no opportunity for them to attract water molecules, and therefore most covalent networks will not dissolve, which is a pretty good thing for beach sand. So if we look at something like diamond, a good example of a covalent network It has carbon arranged in a lattice structure. It's very hard, lustrous, is a beautiful crystal shape, and it's the hardest substance that we know, used for jewelry for its beauty and also for drills for its hardness. Thanks for watching.